The second law of thermodynamics can be expressed in a number of equivalent ways. The first expression that I've stated here on the key concept slide is that heat cannot flow from cold temperature to hot temperature without some external input of work. We've looked at the example of an air conditioner or a refrigerator, which actually does this, but it has an external input of work. Another way to represent this statement, I've put a picture here of what it means to actually obey the law in terms of this statement. Obeying the law would involve a heat flow from hot temperature to cold temperature. That, in other words, is natural. That happens spontaneously. To do the reverse of that would require the input of external work and concomitant changes to the external environment. The second statement that we've already touched upon in the earlier topics is in terms of entropy. So the entropy statement of the second law is that the entropy change of closed systems is always greater or equal to zero, which can be expressed, as I've done here on the whiteboard, as an inequality, saying that delta S for a closed system must be larger than or equal to zero. And this is in alignment with this first statement because heat flowing from hot temperature to cold temperature represents a positive entropy change. Heat flowing from cold temperature to hot temperature, in contrast, would represent negative entropy change and therefore would violate this statement as much as it violates the statement that we started with. There is also a statement of the second law of thermodynamics in terms of engine efficiency, and that's something we're introducing in this topic. It says here, the upper limit on engine efficiency is represented by an engine that is completely reversible in time. The model that Sadi Carnot came up with for such a reversible engine was based on what is called the Carnot cycle. And from that comes the Carnot efficiency formula, which is listed down here. So this E is representing the efficiency of a Carnot cycle-based reversible engine, or you could just say a Carnot engine. Combining this with this statement about the upper limit would lead to an inequality statement like this. In this case, this E is meant to represent the actual efficiency of a real engine, and it says that must always be less than or equal to the Carnot efficiency based on the same hot and cold temperatures that model the real engine that's being considered.